So in today's session, we'll start with sensorless vector control strategies. As the so, what does a sensorless control mean actually? Sensorless control simply means here, wherein we are essentially removing the speed sensor and the position encoder. So in case of sensorless control strategies, what we do is that we do not use speed sensors and or position encoders. So in sensorless control strategies, we do not use speed sensors and or position encoders. We know that for a speed for closed loop control for closed loop control of any drive, we have for closed loop control of electric control closed loop control of induction motor drives, we need speed sensors for the feedback. But in this case, in case of sensorless control strategies, what we'll be doing is we'll be employing some other numerical tool method for calculation of speed. Uh, so for closed loop control, we still need the speed oblique position feedback, but with sensorless control strategies, we'll not be using sensors. We'll be using some numerical control methods, like observers, as we have already discussed in control systems. We can use observers for estimation of speed. Uh, so it's possible to estimate the speed values from the machine terminal voltage and currents. Fine. So we can estimate speed using values of voltage and currents. How as far as this estimation goes, it's complex and machine parameter dependent. So, what are different types of speed control strategies that are presently uh, so presently, as in literature, we can find the following speed estimation strategies. One is direct synthesis. Second one is slip calculation. Third one is MRAS, we have so there are a number of sensorless control strategies that are available in literature right now. So some of these are the direct synthesis method, the slip calculation method, MRAS, Leuenberger observer, extended Kalman filter, and some others. So let's see one by one. So the first two methods that we have described here, the slip calculation and the direct synthesis, they are purely mathematical in nature. Uh, we know that slip can simply, using this strategy, we can simply calculate slip omega. We can calculate the slip speed using the machine's other parameters as 1 plus sigma. So if we know these other parameters of the machine, where sigma is 1 minus Lm square by LSLR, and Tr is simply Lr by Rr. So if we know all these values, Lm, Ls, Lr, Rr, IQS and IDS, we'll be able to calculate the slip speed of the induction motor. And also we can calculate synchronous speed of the induction motor using this equation VQSS from the equivalent circuit of induction motor drive that we have already derived, the dynamic model of induction motor, VQSS minus IQSS RS times sigma time DSS minus VDS S minus IDS S R of S sigma Q of S raised to power S divided by sigma S square, the magnitude of this. So we have omega E. We can derive omega E and omega SL from known values of voltage and currents. And we need to know the other parameters of the induction motor as well. That's the inductances and the resistances, the magnetizing inductances, the starter inductances, the rotor side inductances. So we need to know these quantities for us to calculate the values of omega E and omega SL. Once we know these, we can simply say that omega r, the rotor speed, we are actually interested in the rotor speed, will be equal to omega E minus omega SL. So in case of slip calculation method, what we do is that using the known values of voltage or and currents, and including the other parameters of the system, these other parameters of the system. In slip calculation, what we do is we calculate omega SL first. We can calculate omega E. Omega R, that's the rotor speed, then will be simply equal to synchronous speed minus the slip speed. Slip speed we can calculate using this above formula, uh, equation number 1, and synchronous speed we can calculate using this formula, equation number 2. So for equation number 1 and equation number 2, we need actually the values of IQS, IDS, VQS, VDS. So we need actually the values of voltage and currents. Uh, then using ABC to decode transformation, we can convert them into their respective quadrature and direct components, as well as we need to know the values of RS, LM, LS, and LR. Once we have these values, we can calculate the values of uh, we can calculate the rotor speed of induction motor. So second method that we can employ is the direct synthesis. In case of direct synthesis, what we do is that we have the state space model of the induction motor with us. So using that state space model, we can calculate the value of omega. So this model can be derived from the dynamic model of equivalent dynamic model of the induction motor that we have derived previously. Uh, so this here is the direct synthesis method. We are obtaining omega r from known values of VQS, IQS, IDS, VDS, extra, and other parameters of the system that include the stator resistances, uh, the rotor resistances, the stator inductances, the rotor inductances, and the magnetizing inductance component. So these equations we can actually uh, derive these equations. We can actually see these equations that we have derived here from the dynamic model of induction motor. So it's essentially somewhat similar to that of slip calculation method. We definitely need all those values of resistances, inductances, voltage, and currents for calculation of uh, speed. So there will be not uh, much difference between the slip calculation method and the direct synthesis method. Both of these two methods are heavily dependent upon the machine parameters. The machine parameters that I'm saying is inductances, resistances, uh, the magnetized inductances, the rotor side, the stator side inductance, all those inductances and resistances uh, tend to vary with time. So these systems do not give us an accurate readings, accurate estimates of the output speed. So the first two methods, the slip calculation and the direct synthesis, both these two methods can be derived from the equivalent dynamic model of the induction motor. And the problem with both these two methods is they are heavily dependent upon the machine parameters. So the third type of sensorless control strategy that we'll be studying is the model reference uh, adaptive system. So the speed can also be calculated using an MRAS, model referencing adaptive system. In short, we can refer to it as MRAS. So using MRAS, we can estimate the values of speed. In this case, the output of the reference model will be compared with the output of an uh, adjustable uh, or an adaptive model, um, such that so long as the error between the two models vanishes to zero. Fine. So we actually have two estimate. We have an estimate of speed and we have an actual value of speed, and we are comparing the two uh, models, the reference model and the adaptive model, until and make sure that the error between the two models is vanishes to zero. So once this happens, the MRAS will be giving us an estimate of speed that will be nearly true to the actual value of speed of the induction motor drive. So this here is the MRS algorithm implementation strategy. You can see that we have two models. We have the adaptive model and we have the reference model. Using the reference model, we are getting an estimate of speed, and using the adaptive model, we are getting an estimate of speed. The reference model gives us the nearly true value of the speed estimate. The adaptive model here is the speed value that we are trying to derive. Fine. So comparing the two outputs uh, here and using some adaptation algorithm that's defined using a set of equations, we can find out that the speed estimate will be much closer to the true value of the motor than what was the case with slip calculation or the direct synthesis method. So we are comparing the outputs until the error between the two models becomes zero. So here the adaptation algorithm that we are using is employing a PI controller for making sure that the error we are trying to achieve this. We are trying to make this error zero. So we are for that we have used an algorithm, and that algorithm is based upon a PI controller. Now, as far as this implementation goes, um, so while this model is fairly gives us a fairly accurate values of estimate, but the disadvantage with this system is that uh, at zero at lower values of speeds the estimation is inaccurate. So as you can see that this model requires the values of voltage for finding out the values of fluxes. We are actually what we are doing in this adaptive scheme is we are actually estimating the values of fluxes, and from flux values we are deriving the speed values. So, as already established with derivative control strategy, that flux estimate is poor with voltage model at lower speeds, owing to uh, the energy being dissipated mainly across the resistances and very least amount of energy being used for establishment of flux. So, at lower values of speeds, this model will not give us an accurate estimate of speed. Mm, so we can make uh, so we can say that this model is gives us a fairly accurate values of speed, but at lower speed its accuracy tends to deteriorate. uh, so this is about the model reference adaptive system. So there are two state space models here, the reference model and the adaptive model. The reference model gives us the true values of fluxes, psi dr and psi qr, and the adaptive model gives us the estimated values of psi qr and psi dr. comparing the and we make the comparison between the two flux values, um, and the algorithms, the adaptation algorithm that we try to use here, make sure that this error is actually uh, zero. So these are the first three control strategies, first three sensorless control strategies that we have studied today: the self calculation, the direct synthesis, and the model reference adaptive system. So as far as the rest of the strategies go, that we'll see in the next session.